So today's lesson is on maximum and minimum values. So we're going to start off by looking at this graph and just kind of pointing out where all the maximums and minimums are for this graph. So when I look right about here, this looks like a maximum. All my maximums I'm going to call local maximums because they're kind of local in that area. And then we're going to kind of focus on the global maximums and minimums after. Over here, I kind of see a low point, so I'm going to call this a local min. Again, I see another high point. I'm going to call this a local max. Now, when we're trying to classify whether these maximums and minimums are local or absolute, you want to try to decide if it's the highest point you see on the graph altogether or if there's points that are higher than it. So for example, this point here would be called our absolute max because it's the highest point on the entire graph. Now this one here is only a local minimum because the function keeps moving down, so the lowest y value that you see would be something like negative infinity. Okay, now all of the maximums and minimums we see, you should notice that at those values, the slope is 0 there, 0 there. Now, because this is a cusp, the slope is undefined. So if I were to use my D1 formula, my limit definition for a derivative, that limit would not exist because the limit from the left and the limit from the right would not be the same. Now, the point of this lesson is to find where these local maximum and minimum values are using derivatives, and also to classify whether they're absolute or local maxes and mins. Now, when we're looking at these values, an absolute max will be the absolute max if that y-coordinate, this is the y-coordinate of that maximum, is higher than any other x or any other y-coordinate for that function. So the f of c, which is the point I'm trying to decide if it's my absolute max or min, has to be the highest point in the entire graph. Likewise, my f of c for an absolute min has to be smaller than all other points on the graph. And I mean, when we're referring to all other points that are in the domain of the function. Okay, now the f of c value, which is the y-coordinate, would be a local maximum. If it is higher, that point has to be higher than other x values, other y values, only when we're near that x coordinate. Okay, so in a small area, it's the highest point, but in terms of the entire graph, it's not a high point. A local minimum means that that point has to be lower than all of the other y coordinates, but only specifically when we're near that value. So for example, this point would be a local minimum because it is kind of a low point. So you can see that there are other coordinates that are higher than it on both sides, but it's not the lowest point because this one is the lowest point on the entire graph. But in this kind of small window, it is like a minimum. Same with the maximum. In this local window, it is a maximum because it's a high point over here. It's higher than the points that are around it. But when you look kind of globally, there is no absolute max because the graph goes up to infinity on the left here. So when we look at this example, you can notice that the domain that the function has is only between -1 and 4. So you can see that I've stopped my graph between -1 and 4. And I give you a quartic function, which is just our power 4 function. The graph is already drawn here for you. So in this question, the point is to look at the graph and be able to identify the local maxes and mins and the absolute maxes and mins. So locally, a local min at 0, 0, because it's a low bump on the graph. There's a local, but it'll be called an absolute min at 3 and minus 27 because it's the lowest point on the entire graph. And if we look at the local maxes, there's a local max at 1 and 5. Now globally, the absolute max is sort of like a fake maximum. I'm going to kind of call it a fake because it's really not a point where the derivative is 0 or undefined, but when I look at the graph globally, the highest point I notice is 37. So -1 and 37 is the location for where that absolute max is. But if I were to open up the domain, this would no longer be a maximum because this graph is likely to keep going on up forever. This value is no longer a max. So you have to be careful with these things called fake maximums. They can kind of occur at endpoints. And they're kind of like fake maximums because when you look at it, it looks like a maximum. But again, if you were to open up the domain, that point no longer has to be a maximum. Now with these examples, we're just going to kind of visually go through and decide where are my maximums and minimums. So visually, my graph cosine x starts at 1, it goes high, middle, low, middle, high, and it has that periodic pattern. And then it repeats itself and repeats itself. So I'm going to just kind of go like this so we know it repeats. So there's going to be a local max at, so the maximum value for cosine is 1. Where does it occur? Well, this is 0. This is 2 pi. And it repeats itself every 2 pi units. So my local max is at 1 when x is some multiple of 2 pi. So I'm going to call it 2 pi n when n is an integer. My local min is at -1. We can continue to describe those, but it may not be necessary if we're only looking for local maxes and mins. But in this example, these also work out to be our absolute maxes and absolute mins because they're the highest and lowest points on the entire domain of the function. And these ones would not be called fake maximums or minimums in my sense because they are maxes and mins on the entire graph. When we look at the graph of y equals x squared, you kind of want to ask yourself, what is the highest point you see? Now, because these are going up to infinity, there is no maximum. So I'm going to say no local or absolute max. There's no little bumps or hills or valleys or anything like that for a maximum. I should call that maximum. Now you can see there's a point here where the derivative is 0. We can kind of see that that's a low point on the graph. So there's a local min at 0, 0. But in this case, this also ends up being our absolute min because it's the lowest point on the entire domain of the function. When I look at the function y equals x cubed, I would ask myself, where is the highest point on the function? Well, the highest value I'm going to hit is probably somewhere up in infinity. The lowest value is -infinity. There's no little bumpies anywhere. There is a point, though, where the derivative is 0, and it'd be right at the x-axis at 0, 0. But at that point, there's still no max or min because it's not the high point in that vicinity or the low point in that vicinity. So in this question, there is no max or min of any sort, no locals nor no absolutes. Now, this is kind of your first big theorem. This theorem is called the extreme value theorem. What it tells you is that the function has to have a maximum and a minimum on a closed domain, provided that the function is continuous. So function that is continuous will always have an absolute max and or min, both of them, on a closed domain. So the domain has to be closed. So you have to have sort of like the function stopping. You don't take that function on to infinity. Provided that it's continuous, it's going to for sure have a maximum and for sure have a minimum. Now these maxes and mins will occur either at a critical point, which we'll define soon, or they will occur at an end point. So let's look at the first example. Function is continuous on the interval a to b. It's continuous. I look, where is my absolute max? There is my absolute max. That one occurs on a critical point. Where is my absolute min? There's my absolute min because it's the lowest point on the entire graph in that little section. Okay, this next example, the function is continuous on the closed domain. Here's my absolute max. Here's my absolute min. Okay, in this example, you can see that these two are both absolute maxes because they have the same high value for the entire graph. There's two locations. There's one absolute max at that y coordinate, but they have two different locations for the x. Here's my absolute min. Now the next two examples are going to illustrate that if your function is not continuous, there doesn't need to be a max and min on the closed domain. So you can see here, this one does have an absolute min at an endpoint, but over here, there's sort of no absolute max happening. Okay, there's sort of a open circle here, kind of like a POD. And that kind of point of discontinuity, you can sort of take these y coordinates to be anything, but we don't even know what that y coordinate would be as x approaches 1 because it's kind of an open circle at 3. And the limit doesn't even exist, so it can't be continuous. In this example, you can see that this function is going off to infinity. And there's even a POD here. There doesn't have to guarantee a max or min. This function has no max nor no min. Now basically, like we described before, the extreme value says that we have to have a continuous function, has to be on a closed interval. It will for sure have a max and a min, but it does not tell us how to actually find these maxes and mins. So what we're going to do to find the absolute maxes and mins is we're going to kind of follow a little process. First, we need to find these things called critical points. So I'm going to find critical points. I'm going to abbreviate it CP. And these critical points are the points where the derivative is 0 or the derivative is undefined. So when the derivative is 0, you get these little bumps happening. And where these little bumps are happening could be potential maxes and mins. There's another bump happening. But there could also be a max or min where there's a cusp here. And where the cusp occurs, the function is continuous, but it's not differentiable at that point. But that's okay. It still ends up being a cusp. So on the derivative function, you would use your rules to find the derivative, and then you would just look for where that derivative is undefined. So you may have to look at a denominator. Now you'll notice here that the maxes and mins appear to have tangent lines that are horizontal in nature. So that means the slope is 0. We were talking about these lines being horizontal. And we know that the derivative is 0 at those points, but it could also happen that the derivative is undefined. So you can see in Fermat's theorem here, they mention that the derivative exists. So the only choice is that the derivative would equal 0 where there could be a potential local max or min. So if there is a local max or min, the derivative had to be 0 there, provided it existed, or the derivative could be undefined. So they go through an example here with us. So here's my cubic function. I take the derivative, set it equal to 0. So 3x squared equals 0. So that would mean x is equal to 0. When x is 0, y is 0 cubed, which is also 0. So that tells me that the derivative of 0 is 0. So this is a point where the slope is actually 0 at that point, but it doesn't have a max or min. So just because, so if f prime of a number equals 0, this does not guarantee, does not mean there has to be a max or min. There's just a potential to have a max or min. So this is a big idea to keep in mind. Just because I have a derivative equaling 0 at some point doesn't automatically guarantee that is going to be a max or min. It's just a potential place where there will be a max or min. Okay, so in this specific example, just because we got that point where the derivative is 0 just means that there's a horizontal tangent at 0, 0. That may not, be important, but it's just a characteristic of that cubic function. Now, this example is going to illustrate that even when a function has a cusp and the function's continuous but not differentiable at a point, so you can see here the f prime of 0 will not exist because at a cusp the derivative doesn't exist. It can still be classified as a local max or min provided it is in the domain of the function. So the absolute value of x has a local and absolute minimum at 0, but there is no derivative at x equals 0 because it was undefined. So we know that the slope of this line would be equal to 1, and we would know that the slope of this line for all values less than 0 would equal -1. And we did an example like this in class earlier. We know that absolute value of x is a piecewise function, so there's sort of two pieces happening. If I were to take the derivative of that function, this is the first time I'm showing you this, so we could do the derivative of x, which is 1. We could do the derivative of negative x, which is -1. But then these conditions mean that we have to drop the equality. So the point is if you want to check the derivative at 0, you would need to check that manually. You can't use the rules to check the value at the connecting point. So you can use rules to do this. This is the first time I'm showing you that, but that kind of connecting point still needs to be analyzed individually. And as I approach 0 this way, the slope is 1. And as I approach 0 this way, the slope is -1. So we know that the derivative will not exist. Now again, this is where we have to be careful. We have to be careful when we're using Fermat's theorem, because what this tells us is that if the derivative equals 0 at a point, it doesn't have to mean there's a max or min. It could mean that there's a potential max or min. So this is saying that if we do the converse, sort of the reverse of Fermat's theorem, it's not a true theorem, and it's actually false. Okay, and furthermore, there could be an extreme value which is referring to either local maxes, local mins, potential absolute maxes and mins, where the derivative does not exist. Okay, so when we're thinking of how we actually go about finding maxes and mins, we were talking about finding a critical number. And a critical number is where that the derivative is 0 or does not exist. So we need to find all of those sort of critical points. And then if the function has a local max or min, the value at that point needed to be a critical number. So it either had to be a point that the derivative exists or is undefined, but literally that tells us that for any function we take, if I find the derivative, set it equal to 0, or set it to find where the points the derivative does not exist, those are the only points that will be potential maxes and mins unless I close off the domain, and then in which case the endpoints could be maxes or mins. Okay, so let's go ahead. This example says find the critical numbers just as a practice. So we need to take the derivative of the function. Now there's sort of a product of two functions happening there, so I need to make sure I'm using product rule. So the derivative of the first times the second plus, I leave the first function the same. The derivative of the second is -1. Now, a lot of people have been asking, how far do we go to simplify? We need to turn this into a nice function with sort of one term involved instead of two terms. So the common way to do that is to factor out the smaller of the two common terms. So you'll notice that both of them have an x to the -2/5 in it. I factor out the smaller one. What I'm left with is 3/5. In the first example, my whole variable factored out. In the second example, I need to do some exponent over 5 here so that when I add it to -2/5, I get 3/5, and you'll notice that 5/5 minus 2/5 is 3/5. Usually when these functions are fairly nice, this will turn into a whole number, usually, if the simplification works out nicely. Now I'm just going to clean this up. So x to the 2/5 sits on the denominator. I have 12/5 minus 3/5x minus x. So I'm distributing this out. And now I'm going to clean up the like terms. 12/5 minus 3/5 minus 1 is minus 8/5x. So that's 5/5. So you can make that as 5/5x. And then what you'll notice is because both of them have a denominator of 5, I can pull that denominator of 5 onto the bottom. So 12 minus 8x. The 5 is a term that sort of sits on the denominator, and I have x to the 2/5. So where does the derivative equal 0? I set my numerator equal to 0. So 12 is equal to 8x. X is equal to 12/8. Divide both by 4, I get 3/2. And then where is the derivative undefined? Is what makes the bottom 0. 5x to the 2/5 equals 0, which would mean x would have to equal 0. So that's a critical number, and that's a critical number. Okay. So those are my critical numbers, and then I would proceed from there to find local maxes, local mins, absolute maxes, absolute mins, which we will talk about still. Identify all the relative maximum and minimums of x on the graph below. So they kind of want to identify the location of x where the max or min would be. So let's look at this. So here's a point where the derivative is 0. This is like a local max at x equals a. That point has a bump. That bump represents where the derivative is 0. We keep going, and that's sort of all that's happening. We can kind of look at E. There's another point where the derivative is 0. This is local min at x equals E. And then there's no little hills or valleys, like the function is not continuous here. There's no cusp, function not continuous here, function not continuous there. So there is no other maxes and mins on that interval. Now this is how we actually find a max and min on a closed interval. So we can call this the closed interval method. To find the absolute max or min, We're going to find the critical numbers of the function. We're going to find the function at the endpoints and the function at the critical points. The largest value will be our absolute max, and the smallest value will be our absolute min. So let's go through one full example of actually doing this so you can see what this looks like. When you get assessed on our curve sketching outcome, which I believe is D4, you can for sure expect one of these examples on that assessment. Okay, so first thing I want to find the absolute maxes and mins, so I need to take the derivative of the function, 3x squared minus 6x. I take my derivative and set it equal to 0, which means I take 3x squared minus 6x, set it equal to 0. So you can see here that x will equal 0 or x will equal 2. So those are my critical points. X equals -1/2 and x equals 4 are my end points. So all that I have to do now, and over here as well, there is no denominator. There are no values here that would end up getting solved. So I'm going to do my function at -1/2. I'm going to do my function at 0. I'm going to do my function at 2. And I'm going to do my function value at 4. The largest of these is going to be my absolute max, and the smallest of these is going to be my absolute min. So I'm going to quickly use my calculator to work this out, but on the assessment, you just slow yourself down and plug them in. So this would be -1/2 cubed minus 3 times -1/2 squared plus 1. When I sub that into my function, minus 3x squared plus 1, I get a value of 0.125. When I sub in 0 into my function, I get a value of 1. When I sub 2 into my function, I get a value of -3. And when I sub 4 into my function, I get a value of 17. So here, the smallest value I see here is -3. So that's my absolute min, and it's occurring at a critical point. And this value is my largest value. It's my absolute max, and it's occurring at an end point. So you can see here, if I were to open up the domain of my function, this point would no longer be a point of concern because the function could be doing something different, but this one would still be an absolute min no matter what. And then at the bottom of the lesson, there are other examples you can try for yourself.